Hi, welcome back. We're still talking about measures of dispersion. This is part 3. In our last video, we learned about the variance and the standard deviation. And now we're going to talk about why we're using the standard deviation, which is the value that we will use throughout this class. So the purpose of this is that we can now take a mean and a standard deviation that describes our set. So we now have a middle value, and we now have a value that describes the dispersion or the spread of our data. So we have the middle value and the spread of it. And now we can take two data points from two different distributions or two different data sets, and we can compare them, and we can compare them using something that we call a z-score. And the z-score is calculated as the same as everything. It will be whatever data value you have minus the mean of that data divided by its standard deviation. And I've written out here the population and the sample z values because obviously with the population it's x minus mu divided by s because those are the parameters that we get from the population, but from the sample we have our statistics, the x bar, the mean of the sample, and sigma, the standard deviation of the sample. So it's x minus x bar divided by sigma. In either case here, what we're doing is we're taking a data point x, we are subtracting the mean from it, and then we divide by the standard deviation. Okay? Now, we will understand why these are called z-scores later on, as we will use these throughout the rest of the semester after we go through probability. So what is comparing z-scores? Well, I have the following data, which is our testing set for 6 light bulbs. We have the Philips brand and the Home Depot store brand. We have a X bar of 1000 in both cases, so they both have the same mean, but we see that the standard deviation changes. We have a standard deviation of 36.88 for Philips, and we have 114.02 for the Home Depot. And we can, as we have investigated this data set throughout this lectures, this makes sense, right? The Philips brand has a lower standard deviation, it's less spread out, whereas the Home Depot has a much larger standard deviation as it is much more spread out. So if we compare these, say I want to compare the highest value in both, so I want to compare the 1,050 hours to the Home Depot versus the 1,150 hours. We can see that if I do the Philips brand, I get 50 divided by 36.88, or I get a value of 1.36. You will see throughout this class that we will always round z-scores to 2 decimal places. Home Depot, we do the z-score again. We get 150 divided by the 114, and we get a value of 1.32 standard deviations. So just looking at these two, we can see that the Philips brand one, even though it's 1,050, it is further from the mean in its distribution than the Home Depot one, which is actually closer to the mean. They're very close to being the same amount, but we can see that the Philips is 1.36 standard deviations from the mean versus the Home Depot, which is 1.32 standard deviations. So that we can now compare these two, and we can compare them to their respective distributions, and we can see that the 1,050 is further away from the mean than the actual 1,150 is in the Home Depot. All right, so that's what I've written out here is our conclusion. It is a fewer standard deviations from the mean than the Philips brand. This brings us to a couple of rules, and you will need to understand these rules. You should memorize these so that you know them and you can use them on tests. The first rule is known as Chebyshev's rule. So in the previous lecture, we talked about skewness in data. We call this the shape of the data. And Chebyshev's rule says that if we have any shape of data, so this means if it is symmetric, if it's skewed left, skewed right, etc., we have some information that we know. At least 75% of the data is within 2 standard deviations from the mean. At least 89% of the data is within 3 standard deviations from the mean. And at least 95% of the data is within 4.5 standard deviations from the mean. So no matter what shape of distribution I have, I know 95% of my data will be within 4.5 standard deviations of mean no matter what. All right. It says at least 95%. Remember, these have the at least in front of them. So at least means that value or more. So we may get more data with less standard deviations than is listed by this rule, but these rules take place for any distribution. So the at least says this value or more. And why is that important? Well, as I mentioned before, that we will talk about symmetrical distributions, or as we call them, normal curves or normal distributions. And we get something that is known as the empirical rule. And the empirical rule, if we know our distribution is shaped this way, tells us where our how much of our data lies. So a normal distribution will have a 68% of its data lie within 1 standard deviation. Well, what does that mean? That means from -1 to +1 here, which is standard deviations. So our mean is right here at 0. If I go -1 standard deviation to +1, I get 68% of my data. All right. If I go 2 standard deviations, so I go from here and I go out to 2 in either direction, it's 95%. So it includes the green and the blue to make all 95%. And then if we go 3 standard deviations, we get 99.7%. So red, green, and blue add up to 99.7%. Okay? So things to note here is that this is a special symmetric distribution. So hold on, let me get my pen. With this being a symmetrical distribution, I'm just going to draw the line down 0, and it's not straight, but we have 34% of the data here on this side and 34% of the data here. Okay? And it is symmetric, so it continues to break down just like that. So if I do here, this green is 13.5% of the data. And then these little red areas are 2.35% of the data. Okay, and that is because this is symmetric, so everything is the same on either side of that line. Okay, this will be important. We're going to do 2 examples of this on the next slide using this empirical rule, but you can also use Chebyshev's if you don't know it's normal, because Chebyshev's talks about any distribution and then will give you the number of standard deviations. So given the Philips brand light bulb is normally distributed and has an X bar of 1000 and a sigma equal to 3688, use the empirical rule to determine the boundaries where 99.7% of the data lies within. Notice here, it says it's normally distributed, which gives us that symmetric distribution. So what do we know about this? From the empirical rule, X bar plus or minus 3 sigma is where 99.7% of the data is. So let's do that. Basically, all I want is a lower bound which is my mean. So that's 1,000 minus 3 times my standard deviation, which is 36.88. I can then use my calculator to calculate that. 1,000 minus 3 times 36.88. And I get 889.4. Okay. My upper bound is going to be 1,000 plus 3 times 36.88. So 1,000 plus 3 times 36.88. And here, 1,110.6. Okay. So this gives me the following interval. And that is my answer. Okay. Now, I have a second problem here, and it says, given that the Home Depot brand lights are normally distributed and has a mean of 1,000 and a sigma of 114.02, use the empirical rule to determine the boundaries where 68% of the data lies. All right, I will suggest you pause the video here. You find the lower and upper bound and create my interval. And then when you come back, I will do the problem. So go ahead and pause the video now. All right, let's go ahead and do the problem now. Let's see what we have. So I have a lower bound. We know from the empirical rule that this is x bar minus sigma. So here I'm just doing 1,000 minus 114.02. And then my upper bound is x bar plus sigma. And that is 1,000 plus 114.02. Okay. Why did I do one standard deviation? Because that was 68%. And our empirical rule says it's one standard deviation, so that's why I'm adding and subtracting the 114.02. So let's use our calculator. 1,000 minus 114.02. I get 885. Actually, I get 886. So it's rounding it to one decimal place. And then I'll get 1,000 minus 114.02. And I have to add it. I did a subtraction again. So I will get this value, which is 1,114.0. So this is just 886 to 1,114. That is my final answer. Okay. Thing to note, square brackets mean include those numbers in an interval, whereas parentheses means do not include. So if I had a parentheses there, I would not include 886 or 1,114 in the interval, but with the square, I include those values. So that's why we have the square brackets versus the parentheses. All right. That ends our measures of dispersion. Make sure you learn Chevyshev's theorem. Make sure you learn the empirical rule. And we will be using those to determine how much of our data is between certain values. All right. I'll see you next time.